Welcome. In this lesson, we're going to talk about vectors. Vectors arose from the need to better describe how objects move. They have magnitude and direction, but they're not as concerned with where something starts and stops. Instead, they're more concerned with the direction and the length, usually speed, of something. Time, mass, and temperature are all scalar quantities. A number is enough to describe them. But if we want to describe something like throwing a football, well then simply knowing the speed is not enough. We also need to know which direction we threw it. This idea is worth some further discussion in your classrooms and may even lead to a nice discussion or debate of vector versus non-vector quantities and having your students justify which things would be vector quantities and which things might not be. A common example to help students understand vectors is the idea of kicking a ball in the air. As soon as the ball leaves the kicker's foot, it has two components, a horizontal component and a vertical component, which are independent of each other. The horizontal component has no forces acting on it, absence air resistance, but the vertical component has gravity acting on it. And at any point in the flight, we can calculate the horizontal component and the vertical component, and by putting them together, we can get the magnitude, which is the speed that the ball is actually traveling. Before you move into the more computational aspects of vectors, make sure your students understand really what the concepts are here. You may want to ask questions like, where is the speed minimum? Where is the speed maximum? What does a negative speed in this situation mean? Different problems lend us different things, but making sure that your students understand the real conceptual ideas behind vectors will make all of the computations much easier later on. Basic vector operations are very simple, as long as your students understand the independent nature of the components of a vector. Once you understand that the x and y components are separate, then adding two vectors makes perfect sense. You add the x components, you add the y components. One area of confusion for students is the idea of component form of a vector. Students wonder why we choose to draw vectors starting from the origin. An example of this is the idea that the wind is blowing southeast at 10 miles per hour. Well, we have a magnitude and a direction, so southeast at 10 miles per hour, that vector can be placed anywhere and have the same meaning. The only time where you wouldn't want to do that would be if you, for example, put wind gauges all around your city and measured each one for magnitude and direction and wanted to compare them. If the vector position has some meaning, then of course you want to preserve it. But otherwise, we don't worry about that and we generally draw all of our vectors starting from the origin. Dot products and cross products are two important ideas with vectors. Now here's where we as teachers have to really thread the needle between building deeper understanding and acknowledging that not everything we teach can be proven to our students. First, it's important that your students understand that a dot product gives a scalar quantity while a cross product gives a vector quantity. There's one key concept that your students need to understand, and that comes from the formula u dot v equals the magnitude of u times the magnitude of v times the cosine of the angle between u and v. As your students know, the cosine of 90 degrees is 0. So we can see that the dot product here is really a measure of how parallel our vectors are. As the dot product approaches 0, the angle between them approaches 90 degrees. Essentially, the smaller the dot product is, the less parallel or the more unparallel our lines are, which is essentially perpendicular. Let's take a look at the dot product formula as if we had no idea what a dot product was. This will give your students a little idea of how the dot product became such an important measure. We begin with vectors a and b, where vector a has components a1, a2, and vector b has components b1, b2. Now drawing them with their initial points at the origin, we can complete this triangle by drawing the vector a minus b, where a minus b has components a1 minus b1 and a2 minus b2. Now, let's apply the law of cosines and focus on the angle between vectors a and b. The law of cosines tells us that the magnitude of vector a minus b squared is equal to the magnitude of vector A squared plus the magnitude of vector B squared minus 2 times the magnitude of vector A times the magnitude of vector B times the cosine of the angle between them. All right, now let's substitute some of our components into this equation and see what happens. The magnitude of A squared can simply be A1 squared plus A2 squared. And the magnitude of vector B squared can simply be B1 squared plus B2 squared. Now, let's consider the magnitude of A minus B squared. As you can see, the square is going to cancel our square root. And by expanding, we're going to end up with A1 squared minus 2A1B1 plus B1 squared plus A2 squared minus 2A2B2 plus B2 squared. All right, now let's take all of this and substitute it back into the original equation we started with from the law of cosines. As you can see, after we simplify some things, we end up with negative 2A1B1 minus 2A2B2 equals negative 2 times the magnitude of A times the magnitude of B times the cosine of the angle between them. Finally, by dividing by negative 2, we end up with A1B1 plus A2B2 equals the magnitude of A times the magnitude of B times the cosine of the angle between them. And of course, this is our dot product formula. So if you do all of this work and you don't know what a dot product is, you look at A1B1 plus A2B2 and you think, well, that must have some significance. And this is where the idea and the importance of the dot product comes from. Unlike the dot product, which is a scalar quantity, the cross product gives a vector quantity. This vector has one important feature in that it is orthogonal to both of the given vectors. Orthogonal is essentially perpendicular in 3 dimensions. So if you think about perpendicular makes a 90-degree angle, well, that doesn't exactly work anymore when we talk about 3D. If you think about a line and you ask your students to draw or to find a line that is perpendicular to it, well, eventually they're going to figure out that there are an infinite number of such lines that can be perpendicular, make a 90-degree angle. So when we talk about orthogonal, what we're really saying is we have 2 vectors, and those 2 vectors create a plane. They exist in some plane. Any 2 vectors exist in some plane. And we are now going to find a vector which is perpendicular to that plane. And that is the orthogonal vector. It's perpendicular to both of our given vectors. Below you'll see an applet which you can play with, which has 2 vectors which you can move around, and which automatically creates the cross product, or the orthogonal vector. Consider what happens when you take your 2 vectors and make the angle between them almost 0. Or what happens when you make the angle between them about 90. Or what happens when you make the angle between them about 180. All interesting observations that you can share with your students. 3D vectors can be difficult for some students. But sometimes difficulty is in how we teach something and not actually how difficult it is. Why not begin from the very beginning with teaching 3D vectors? Because what is a 2D vector if not a 3D vector with a z equal to 0? Now it's important to note that none of what we've done here is truly a mathematical proof of these ideas. But these simple explanations will help to build dramatically better conceptual understanding of these ideas than by simply saying, oh, this is the dot product and it gives us a number and here's the formula. If nothing else, we've built a basic level of conceptual understanding and context around these complex ideas.